So, welcome back. Our next talk is Unconventional HDL Synthesis Experiments with Pepin, and let's go.
Hello everyone, I hope you are all enjoying the remote congress. I'm going to give a presentation about unconventional HDL synthesis experiments, like taking a spreadsheet to 7-4 logic chips. My name is Pepin de Vos. I have a background in software and a degree in electrical engineering, and my personal mission is to write better open source tools for chip designers. Here you can find some links to my social stuff, my Patreon and Twitter and website, GitHub, all the things you might want to see or not. So what I want to talk about today is, well, first an introduction of how synthesis for FPGAs and ASICs normally work. Then I want to talk about the open source tools that are available. And finally also a bit about, well, mostly about the unconventional synthesis of spreadsheets in 7-4 series logic. Conventional synthesis, usually from some HDL like Verilog or VHDL or System Verilog or what have you, to a bitstream for an FPGA, or sometimes if you're like an IC design company to ASIC. And here's an overview of how it works for an FPGA. So you have on the left the HDL languages, which get fed into a synthesis tool such as Quartus or Yosis in the case of this talk, but yeah, mostly in commercial FPGA stuff it's Quartus and Vivado and ISE. These output like some netlist format, which can be eblif or JSON or ediff or whatever you call them, which then get fed to a place and route tool such as NextPNR or Verilog routing or Vivado IC Quartus. And these take sort of netlist of the logic of your circuit that we'll get to in a minute, and figure out how to place them on the chip or on the FPGA. In the case of the commercial tools, they just output a binary onto the FPGA. In the case of the open source tools, it's frequently a separate step where first you have sort of like assembly language for FPGAs, and then you use these chip-specific place and route or like bitstream generation tools. For ASIC it's a bit more tricky, of course, because you're designing this whole chip from basic logic cell blocks that you just place on the silicon. So it also starts with like the synthesis, but then there's an whole the timing analysis, and the place and route is a bit more involved. You take several loops through the design iteration, and finally you get this GDS file, which is sort of like basically a picture of the mask layers that you want to get on your chip. The important thing is in an ASIC you synthesize to a standard cell library, which is just like transistor blocks that you can actually put on an IC. Whereas with the FPGA you synthesize to sort of the lookup tables and multiplexers and flip-flops inside the FPGA in a fixed way. So here's a simple Verilog program. I think it's just like a counter which blinks an LED with the highest bit. Actually 8 bits. And like the way this gets synthesized, if you go back you can see there's two sort of statements in Verilog. One is sort of the combinational statement, which gets synthesized into Boolean logic. They're just like, these are the inputs, it will perform this logic operation and you get the output. And then there's a sequential code, which is flip-flops, registers, which take the input, and then on a clock edge it copies the input to the output. And a way this is frequently sort of represented as a mealy or a more machine, which differ in some sort of like the output and input a little bit. But the key thing is, you have this transition logic, which is your sort of translates the previous state into the next state. So you have the state memory, which on each clock edge copies the input to the output to the new state, and this new state then goes into the transition logic to compute the next state. And this abstract logic system, you then convert to the technology specific primitives, which in an FPGA are basically a lookup table, which is basically sort of like, if you have these truth tables for a logic function like an AND and OR, you just put this in a small memory of like 16 bits, for example, in the case of a 4 input LUT. And then there's like a hard-coded, physical lookup of a flip-flop, and a lot of multiplexers that connect this particular, they're called slices, this LUT flip-flop combination, to adjacent flip-flop slices things to make the routing. In the case of an ASIC, of course you're more free to do whatever, because you can just design the silicon yourself. So there you have the standard cell of different logic operations and that kind of stuff, and flip-flops and all sorts of other things, and you just have to place them on the specific location that you want. On an FPGA, these the logic cells are already there. You just have to connect them in the right way with these multiplexers. And in the ASIC, it's of course a bit more different. You have just you have your silicon chip, and you just have different layers that you draw your cells on, basically. So now on to the open source tools that are available. Was already in the first slide briefly. Yosys is the main synthesis tool currently in the open source system, and there's an architecture that's based on small commands. So you just have you can sort of write a script to chain together different compiler passes, basically. Scriptable, so you can make your own scripts for different passes, and this is frequently it's done for FPGAs for different FPGA primitives, of course, but also for ASIC you frequently want to tweak the stuff it generates, and if you want more area or more timing or whatever. It comes with a bunch of scripts for the different FPGAs that it supports, so you can just say synth, go in, IS40, Xilinx, Altera, everything. And these use a library of primitive cells that are supported by this device, and that are either in a specially annotated Verilog file or a Liberty file. In the case of ASIC this is more common, which also contains timing, and we'll get back to Liberty files a bit later. The interesting thing about Yosys is that it has an open, it's open source, and there's an intermediate language. And this is really cool because now you can develop new programming language that target this intermediate language instead of compile to Verilog usually, as was usually the case in the past. But of course then Yosys can output Verilog, so you can still integrate it in your commercial toolchain if you want. NextPNR is the the most widely used open source place and route tool for FPGAs. It has this architecture of you just implement this API that it has in C++, and you do this for each architecture that it supports, and it currently supports only a few. Like the mature ones are IS40 and ECP5, which are both lattice FPGAs. There's some work in the background going on to add support for more FPGAs, one of it which is my work on the Go in FPGAs, which is another talk I will be presenting at this conference. Yeah, and that's it. Last thing I want to talk about briefly is NMedian, or I don't know how you say it, but it's this new hardware description language that's similar to Chisel, Spinal, HDL, and Clash, and many others. Most of which usually compile to Verilog or VHDL. NMedian actually compiles towards the Yosys intermediate language, which is interesting. But it's a Python DSL, which makes it great for generating code on the fly with a Python script. That's what we're doing later. That's why I wanted to mention it here. So now on to the main part of this talk, the unconventional synthesis, when you don't go from Verilog or VHDL or whatever, and don't go to FPGAs, but you go to something stranger. And this is, like, in my opinion, the great thing about this open source ecosystem. It allows all these crazy things to happen, basically. So, I mean, this is just something I and a friend did. But yeah, it's just an inspiration for everyone to try their own crazy things with these open source tools. Invent new languages, new targets, new everything. Do what you want. So, Excel. It's used for many things it was designed for, and probably also some things it was not designed for. Which is interesting. You see frequently jokes about, fusion power plant on Excel or whatever. But at the moment Excel is, this desktop application. You can't just put it in some hard real-time industrial context. It's sort of like a human in the loop system more at the moment. So what if a spreadsheet could run under a millisecond on an FPGA? I think this might be interesting, because frequently the people that write the HDL, the program, the FPGAs, are not the domain experts who know everything about the process they're working with. So if the person who is the domain expert can also modify the code that's running, it might lead to shorter feedback loops. So maybe there's some actual use for this, but it just started as a joke, basically. So we'll see. The plan is, you remember this more meaty machine, transition logic, state memory, and this is the plan. Because Excel is kind of, you put some data in the cells and some other cells update, which is kind of like transitional logic, where you just, you change the inputs and the output change. Excel is not so great for the state memory, because there's no loops or like dynamic programming in Excel. You can do it if you if you make a circular reference in Excel, it does this like ref error thing. You can actually still run these Excel sheets in my compiler, and they sort of loop, but it's kind of awkward, so it's not really convenient to use it in this way. So I think the focus is like this transitional logic, where you just like tweak the coefficients of your industrial plant or whatever. Pretty neat. So the basic idea is pretty simple. You have this example spreadsheet here. It's just like a bunch of numbers, then I add, multiply, sum, whatever. And this is fairly straightforwardly translate to a Verilog assignment statement, where you just say, oh, this sells this, and you just have to dereference the cell reference, basically, and it looks pretty trivial. Except this the second to last one, where it gets a floating point number, and this is a bit challenging, because FPGAs, they work in like bits and binary, and doing floating point math takes a lot of area, very slow, very inefficient, very nasty. So this is a problem. The other problem is this sum function. We need to implement it, basically. It's not an overcomable obstacle, but it's something to do. Yeah, so this is basically the steps to get from A to B. We have to write a parser for the Excel sheet, and luckily there's like a Python library for Excel parsing, and there's this parser library called RC3, which I use to further make an abstract syntax tree of the formula in the cells. The floating point issue I solved by writing a fixed point number class that keeps track of, you used to okay, I have this many bits of float and this many bits of integer, like fractional and integer bits, and it keeps track of, like, if you add it, it needs an additional bit of integer width, and if you multiply two numbers, you need twice the bits on each side. And of course you can downcast it again, because otherwise it quickly runs out of control, but it keeps track of where the dot is in a number, basically. And then you need to implement Excel functions, and there's like hundreds of them, which is a lot, but okay. And then the last step is just generate. If you use Python scripts, you generate some Python code that makes this engine generate Verilog in the end, or simulate it, or whatever you want to do with it. Here you see the parser. I parse like this cell expression as just an addition of A and B, and you see you get this tuple with the operator and then a range reference, which can reference to another sheet, and also includes the boundaries of the reference. And then the second example is I parse a sum function which takes the range, and then you see, okay, it gets this function class that I made, and then that's the name of the function, and the argument, which is again a range, but this has one range with the boundaries. And you can make it as complex as you want. You can have nested expressions and everything. Then the fixed point number class, which was a bit challenging to write, but not too bad, because an engine has this idea that you're not supposed to like subclass their own number class, so you have to sort of wrap it and then implement all the the operators as wrappers over the internal operators. The hardest part here was there's this concept in Engine that's called like an array, which is like a normal Python list, but you can index it with a logic signal. And wrapping this in a fixed point was a bit challenging, because you have to like unwrap the thing to the number and put that in the underlying array, and then if you have nested arrays, like if you have a square cell reference to another reference, and it gets a bit complicated. But in the end I sort of managed to make it work. And here in this example you see I make this number from a floating point which I set to pi, and that's 8 integer bits, 16 fractional bits, and it's a signed number. And then I do the same again for Euler's number, and then I add them, and you can see the result of that is an Engine abstract syntax tree expression, which is the constant that's 24 bits wide signed, and has this following contents in it. And then there's a plus operator, and then that's again wrapped in my Q fractional number class, which now has 9 integer bits, because I did an addition, and the addition of two numbers can be twice as big as the individual thing, so you need an extra bit. And then I have this little helper that starts the simulator, inputs the number and evaluates the result and converts it back to a floating point. And then you see that indeed it added pi, which is like 3.1 blah blah blah, and Euler, which is 2 point blah 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 blah, which is 5 point something apparently, which seems approximately right. And then you need to implement all the Excel functions, and in my case only really some is implemented so far. I started implementing division because, so Yosys, it will try to synthesize a combinational version of multiplication, division, whatever. But division is kind of a complex operation, so if you just tell it to implement division combinationally, it will generate some huge code that's very slow. So it's better to have a division function that takes like a cyclic multi-step division algorithm. And also the Python modulus and Verilog modulus are different. So it doesn't like it when you do signed divisions because it's the semantics between Python and Verilog don't match. So this is kind of work in progress still, and the other functions, it's just you have to write this Nmgin code to implement them, which is some work. So if anyone wants to do 200 of them, enjoy. For this, unless someone hires me to run this on their power plant, I don't think I will implement all 300 of them. Then the last step, generate code. I won't show you all the code on this slide, but just to show the result. On the left you see the spreadsheet that I edited in LibreOffice and saved as an Excel sheet. And then in this case I simulated it in the Python simulator that Nmgin has. And you can see then I can load this into the GTK wave, the simulation results, and you can see the numbers progressing. And this last sum, it takes a sum of the whole block, which takes a cycle for each cell. So you see it takes a while, but in the end, the result on the left is 653 and the result on the right is also 653. So it works. Pretty cool, pretty useless, but just having some fun. Profit? So it started as a joke, and I have this idea there must be so many people using Excel, there must be some crazy application for this, but so far everyone I talked to was we already have developers and no use for this, so who knows. For now it's just a fun thing I did. And now on to the next thing. I had this idea in my mind a while ago to just as one does, design my own CPU in 7/4 series logic, but I never really got to it, and it seemed like a lot of work. But I thought, what if Yosys could just synthesize some CPU to these chips? And then Dan Ravenstoff came around and actually did it. So I found this tweet on Twitter. I don't know if teaching a new dog all tricks is an idiom, but I managed to wrangle Yosys into synthesizing Verilog into 7 series logic. That was pretty amazing. So we got in a conversation, and at this stage it was just some short script that would output the netlist, and then that was it. Then I joined the effort and helped writing simulation stuff to verify that it actually works, and stuff to actually transform it into a real PCB. So let's get into that, how that happened. Basically, so as I discussed, Yosys works with this synthesis scripts, and for ASIC it uses Liberty files that specify all the standard cells that you have. So the first step, that was what Dan Ravenstoff had done, was write this Liberty file that Yosys can parse and then synthesize your HDL design into a netlist that uses this the specific cells, or in this case the 7/4 logic chips. Then you can use this to synthesize and simulate your designs to verify that post-synthesis they still work the same as we did before. which of course uncovers some interesting bugs. And then sort of the unusual part in terms of, ASIC flows is you don't generate like a GDS silicon wafer file, but you of course want to have a PCB in the end. So I found this Python library that's called Skiddle, which allows you to programmatically output keycard netlist. So yeah, I wrote a script that takes the Yoast output, which can output JSON in this case, and then convert it to a keycard netlist. And then you just have to import it into new PCB or PCB new and make a PCB out of it. So, well, first step is if you go to the 7.4 Logic Wikipedia page, there's a lot of series over the ages. Of course, the older ones are the bipolar ones, and then the newer are the CMOS ones. And looking at the distributor website, like Farnell, Mouser, everything, it seems like the HC series is the most common. And that has the largest selection of chips that you can still acquire in this day and age. But the AC series is a lot faster. So in the interest of making a CPU with a high clock frequency, we decided at first to go with the AC chips. It's not that much different. You can modify it, tweak it a bit to get a different series. Notably, there's also this. We'll get the AUP series. It's like single devices per cell. So normally these 7.4 series logic have 4 or 8 cells in the same package, which is a bit of a challenge for placing and routing your thing. So these single cells could be interesting. You need more of them, but they're much smaller and come in like SMD packages, so it could be interesting also. So step 1 is write this Liberty file basically, and this is a very simple example of what it looks like. In the case of ASIC, it frequently also contains like huge tables of timing information and all sorts of area, power, everything. This is like the bare minimum you need. It's just like, the pins that it has and then the logic function that the output pin has, which in this case is a NAND. So it's like the AND and then this apostrophe means the NOT. And we gave an area of 3 here. Later we experimented with setting the area to the dollar cost or the pound cost or the euro cost or whatever of the chips on Farnell or Mouser. So that would actually optimize for cost in a way, which was an interesting tweak to get a cheap, affordable CPU basically. Here's a look at the Yoast script, sort of very short selection of a few commands at least. And first you read your design, but it's not inside the script. So you read the. Okay, so there's two types of models. There's like the lib files, the Liberty models, which are like you select the AND and OR and NOT gates and all that stuff. But for stuff like an adder, Yoast has trouble mapping to cells with multiple outputs and more weird cells. So there's a few special cases that we implemented as a several technology mapping step, such as adders and counters and these kind of things. We also tried a bit with memory, but that's still work in progress. Waiting for a Yoast patch that improves the memory support to do single port ROMs and RAMs that you would typically find in DIP packages. You read the Verilog, you read the Liberty. Here's a tech map step that maps adders. There's a bunch of other steps and also in the full script, but this is just like an example. Then you call this synth run fine, which takes a generic synthesis script, which just takes your logics and flattens it and converts it to generic low-level cells from the original Verilog stuff. Then there's this diff lib map, which makes a flip-flop from maps the flip-flops from the code to the Liberty flip-flops. And finally ABC, which is an important part of Yosys that does the logic optimization. So you take your net list and then you feed it to ABC, and ABC then converts it to an AND inverter graph and then simplifies it and tries to map it to your specific technology cells. And the 1000 is sort of the delay target. So by setting the delay target really high, it optimizes for area, because in this case, less chips is cheaper, so we really care about the area mostly. And then you synthesize, you take this Verilog, you feed it to the script, and you get this net list, or here are just statistics in this case. You can see it had this counter and XOR and compare cells. And you can, it's kind of funny, like, you can sort of play, there's sort of this code golf game where you try to optimize your Verilog to generate the minimum amounts of cells. And this was really the optimal I could get from this thing by writing like a special counter pass as well. One thing I, for example, noticed was many of the 7.4 chips have an asynchronous reset, while it's common in VHDL and Verilog to use synchronous resets. So by going for async resets, you really reduce the amount of extra logic used to implement these resets. And stuff like that, you just tweak the bits a bit, and you that just this PVM out expression that's really funky to use this one XOR cell to implement it, and this comparator. So this was just a fun code golf thingy. And then there's a boring but important step where you verify that your thing actually does what it's supposed to do. So you write a test bench, simulate the original code, then you synthesize the design, and you do a post-instance simulation to verify the behavior with the synthesized version of the code. And then the final step is generating the keycount netlist. And this is really easy in Skiddle. You sort of make a new part, and it has like the library in keycut that you want to use, and then the specific part you want to use. And you can also assign it a footprint, which in this case is just a dual inline package. And then this chip has sort of like this properties for each in and output port, and you just assign it to a net. So you have these nets, in this case VCC and ground already connected before I return it and assign the rest of the netlist ports. And then finally you import it in PCB new. And so in this case the left hand of the circuit is just like some 555 timers, and for single stepping the logic and tweaking the speed of it. And then the left side is the generated netlist from Yosys. For small designs you can just like route it by hand, but there's also a free router and topper, I don't know how you say it, but it's plugins for keycard that do auto routing. And a lot of PCB designers frown at auto routing, but if you're doing a large scale ASIC type of CPU with hundreds of chips, I think you will like the auto routing. I think some of these can also do like auto placement, but last time we tried it, it sort of clipped them all together and it was a bit of a mess. But maybe that's just a case of making a bigger PCB, I don't know. And then here is a little demo of the final PCB. And this was really cool, you get this... I want to show you, you get this PCB in the mail from China somewhere, and you put all the parts on, and you know this feeling when you write some code and it works on the first try. But this with the PCB, I just put all the parts on and I applied power and it just worked. That was amazing. Like you can see there's this blinky LED that is faded in and out with this PWM counter, and then this knob can adjust the speed of it. And yeah, that was the synthesis of the 7.4 part. And then the final part is, of course, can you combine all the two? And that's pretty easy. You just, you take your spreadsheet, you read it in, and from there you generate Verilog. And then from there it's the same as before, you feed this Verilog to the synthesis script, and then you get this output. I haven't built a PCB for this yet, but you could. In this case you can see that there's a bit of AND gates and stuff, and this is mostly because the flip-flops are a bit broken at the moment, but yeah, basically you can see the adders are there, and it's basically as expected. So what's next? Well, anything. You could try to implement all the functions and run this Doom Excel sheet on it, and of course you need some interfaces as well, but okay. Or you could synthesize a whole RISC CPU with it, and there's this small bit serial CPU called Serve by Olaf Kintern, which is on FPGA like 200 LUTs, I believe. It keeps getting less, but so I don't know anymore. But here you synthesize it to 7.4 logic chips. This case the AUP1 cell blocks, and you can see there's like 800 of them, and at the bottom is what this would cost in British pounds to synthesize, to buy from a distributor. So it's like €300 for RISC-V capable 7.4 CPU. So if anyone wants to spend the money and do this, please let me know. But so far we've just been theorizing about it. And of course, what's next is your crazy projects. But I think that's what it's all about. But that's why I want to give this talk, to inspire people to use these open source tools and improve them and do their crazy stuff with it. And that's it. Thank you.
All right, thank you, Pepin. Now we have a few minutes for Q&A. Once again, as a reminder, you can ask questions on Twitter or Mastodon under the hashtag RC32, where the 3 is a number and the 2 is spelled out. And a similar situation is on the IRC for questions. So we have one question. I'll just read it out. I'm under the impression that there's more movement/progress in open source FPGA land in recent years. If this impression is true, do you have insights why that is the case?
Yeah, as they say, it takes 10 years to become an overnight success. Like the first Ice Storm project is, now going a long time. And yeah, like now it's sort of reaching a point where all the stuff just works. It's just growing and growing and growing, so it's sort of gaining momentum, and now it's become this overnight success after 10 years. I think that's the main takeaway.
Nice. Do you have any projects in particular that you want to highlight, in addition that you haven't mentioned so far?
There's so much cool stuff going on in the open source. I don't know if anything in particular. I'll highlight my Enschede buddies because the Clash language is actually from Enschede, where I am located. So they are doing some cool Haskell stuff where they compile Haskell to FPGA stuff. So that's really cool.
Nice. Yeah, I recently, there's this esoteric-ish programming language called Nock, right? It's like used for the Urbit project, which they're basically trying to rewrite everything from scratch based on functional programming. And they're also considering developing a chip for their weird little functional language, which I find quite interesting.
Yeah, so actually it's looked into it a bit. Everything was quite broken. Implementation, it's more like a virtual machine type of deal,
Yes,
So,
it's very abstract, I would say. Like it's not built around any hardware consideration. It's
right.
built around
So I think it will be
mathematics.
challenging to make a chip for it, but it's an interesting idea.
Yes. So do you have any recommendations for beginners to tinker around with FPGAs?
For beginners, well, I don't know. Yeah, just get yourself an icebreaker and play around, I would say. So the icebreaker is so at the moment the ICE40 is the most mature, well-supported FPGA architecture in the open source tools, and the icebreaker is a quite affordable board to play with FPGA and synthesis and other things.
All right. To a clarification, what I said is it's called NOCK, N-O-C-K. And I think you will find all the information at urbit, so urbit.org. All right. Could it be possible to use your tools to perform computation into FPGA and put results back into a spreadsheet fluently? I'm not sure.
I mean, yeah, you would have to write some plugin for Excel, I suppose, or write your custom spreadsheet program. My thing is pretty generic, so you could just attach like a wishbone bus to it and then feed the data through USB or whatever. But yeah, you'd have to write some GUI to glue all the stuff together.
I kind of feel like hardware accelerated Excel would be a great selling point for you to really make some money in the banking sector.
Yeah, I mean, it sounds like it, but so far I haven't found someone who's going to give me millions for it. So who knows?
Maybe one day.
Yeah.
All right. So I think we're almost out of time. Where can people find you for additional questions?
I'm in the
answers?
IRC and I'm on Twitter and.
I think you're also in the RC3 world, right?
The world at the moment, no, because the first days it wasn't really working for me, so I'm not there at the moment. But yeah, IRC and Twitter work.
All right, it works now. Maybe also as an announcement, it's working quite well now.
Okay, that's good.
All right, do you have any parting remarks before we close this?
Yeah, just have fun with your FPGA and do whatever you want to do. I don't know.
All right. Well, thank you.
Welcome.
Goodbye, everyone. Goodbye, Internet.